So the ideal gas law. Boyle's law, Charles' law, Avogadro's law, and there's also another one called Gay-Lussac's law. Those describe two variables changing. The combined gas law puts three of them together so that we have three variables changing. But we can combine all of these into a single law. It's called the ideal gas law. So this is the ideal gas law. PV equals nRT. It's sometimes affectionately called PIV-NERT. There's no vowels in there, but PIV-NERT. So there we've got the pressure times the volume is equal to the number of moles times R times the temperature in Kelvin. R is a constant. It's just a proportionality constant, essentially. And R has the value 0.0821, and the units are liter atmospheres per mole Kelvin.
Do we have to care about that?
You do have to care about that.
No,
The units? You have to care about the units. You have to care deeply about the units. They're very, very important here. More so than in the other gas laws. So this is always the same, and I'll give you this number because sometimes you have a brain fart and you forget how many zeros are in there or something. I'll give you that number with the units. The units here tell us what the units for the other quantities need to be. Okay? The pressure needs to be in atmospheres. See ATM in here? That's a pressure unit. The volume has to be in liters. There's liters. The amount of gas has to be in moles. There's moles. The temperature has to be in kelvins. There's the K. So you have to use atmospheres, liters, moles, and kelvins when you're using the ideal gas law.
were the guys that created, were they all British?
They were not. They were not all British. That's an interesting question.
Well, because they keep using Kelvin.
Well, they do keep, well, they keep using Kelvin because they were scientists. Yeah. Boyle, I think, was British. Charles was French. Avogadro, I think, was Italian.
So they were close to that.
They were European. Because there was not much happening in the United States in terms of science in the 1600s, because we weren't a country yet. We were fighting with the Indians, trying to survive. So, yeah, it does make sense. If you're interested, this table gives the relationships between these different laws, and here's Gay-Lussac's law. That's the relationship between pressure and temperature. So these are all the individual gas laws that can be used. That's all very nice, but we don't need to do that. So let's learn how to use the ideal gas law, and then I'm going to show you how you can make all of those other gas laws. Actually, I'm going to do that first. I'm going to show you how you can make any of these from the ideal gas law. So you really only have to remember PV equals nRT. So this is what you do. You write PV equals nRT. And then you make fractions and you write PV equals nRT again. So I'm going to call the one on top 1, and I'm going to call the one on the bottom 2. So this is P1 V1 equals N1 R T1. I'm not going to give R a subscript because it doesn't change. P2 V2 N2 and T2. The ideal gas constant R is always the same. Anything divided by itself cancels out. So goodbye R. Okay, so that's what I have left. So now we need audience participation. Pick 2 variables. N and T. Okay, so we're going to have N and T that are changing. Oh, yeah, that works. No, that's constant. Pick one of these. Pick one of these. Volume and temperature. Okay, we'll do this one. Volume and temperature. So the volume and the temperature are going to change. That means that N and the pressure are going to stay the same. So if N1 is equal to N2, then those cancel out. Let's remind myself of what we're doing here. We're doing this one. So the N's cancel out, and the pressure is staying the same. So the pressure cancels out, because the initial pressure is the same as the final pressure. Do we know what it is? Not necessarily, but it didn't change. So anything divided by itself is 1, it cancels out.
Is this showing us the relationship between all of them?
I'm showing you how you can take the ideal gas law and get any of these from it. So what I do is I cross off all the variables that aren't changing. So what I've got left then is V1 over V2 equals T1 over T2, which does not look exactly like this. But if I rearrange it, it does. If I move these two, V1 over T1 equals V2 over T2. Okay? If you don't like that, that's fine. Just look them all up. But you can get them all from the ideal gas law. And there's no need to rearrange into this form before you solve it. This form will work just as well. You just cross off everything that doesn't change, then solve for the thing you need, and go on your merry way. If you have questions about that, I'll be happy to talk to you about it later. Okay, let's use the ideal gas law. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So, we're just going to do what we've been doing. We're going to make a table. I love it when you can always start things the same way and have it be good. So, just going to go on our way. And so the first number I come to, 0.845 moles. And that would be N. N is for number of moles in the gas laws. Pressure is 1.37 atmospheres. So I'm going to label this column pressure. Temperature is 315 Kelvin. Do I need to do anything to that? No, because it's already in Kelvin. The gods are smiling on us. I ran out of numbers. I don't have anything for the second row. That's because nothing's changing. This is just a gas sitting there. So, because I don't have any 1s and 2s, I just have this one set of numbers, I'm going to use the ideal gas law. I don't want to use something that has 1s and 2s because I don't have any 2s. So that means I need the ideal gas law, PV equals nRT. What is the question?
Calculate the volume.
Calculate the volume. Okay, so I want volume. I can rearrange this, and this nice little guy doesn't have any fractions. I can rearrange this by dividing by P on both sides. So the P cancels out. So volume equals nRT divided by P. Well, I've got N, I've got P, and I've got T. What's R? R is that messy thing. R is 0.0821 liter atmospheres per mole Kelvin. Those are just the units on R. So I'm just going to put everything into this equation. So N, 0.845 moles. It's very important to write the units. R, 0.0821 liters times atmospheres divided by moles times Kelvin. And the temperature, 315 Kelvin. All divided by the pressure, 1.37 atmospheres. before you multiply and divide, check your units. Here I've got moles and moles. This is in the denominator here, so those are going to cancel out. Moles are going to cancel. And here I have Kelvin, and Kelvins are going to cancel. And now I'm left on the top with liters times atmospheres, and I'm dividing by atmospheres. The atmospheres cancel. That's why R has those funky units, because they all just cancel out so beautifully. So now I can do the math. 0.845 times 0.0821 times 315 divided by 1.37. Look at all those numbers. They all have three significant figures. 15.9, there's three sig figs. Write down two more. The unit is liters. It's the only one left, and it's a unit of volume, so that's nice. The 5, the decider makes the 9 round up to a 10, so I'm going to end up with 16.0 liters. Any questions? Did I need the table? I didn't need it. Was it a waste of time? No. It still labeled everything for me. Yeah.
How many variables change in the combined gas law?
In the combined gas law, 3.
Okay, so single or fiddle.
Yeah. Now, could you have 4 variables changing? Yeah, you could, but we're not going to give you any problems like that. A tire, 8.5 liter tire, is filled with 0.55 moles of gas at a temperature of 306 Kelvin. What is the pressure of the gas in the tire? So we could make a table, and then we'd find out that nothing's changing. So we could do it that way, or we could say, oh, well, this is giving me, I've got volume and moles and Kelvin, and they're asking for pressure. This is probably going to be an ideal gas law. And so we could also do it this way where we just label stuff. So 8.5 liters. Well, liter is a unit of volume. That must be the volume. 0.55 moles. Mole means this is number of moles of gas. 306 Kelvin, that's the temperature. And it has to be in Kelvin, and it already is, so I don't have to worry about that. And then pressure is what I'm trying to find. PV equals nRT. So the pressure is going to be equal to nRT over V. I need R. R is 0.821. Liters times atmospheres divided by moles times Kelvin. .55 moles. R 0.08201, 821. That's poor planning. Times 306 Kelvin. Sorry about that. Divide by the volume, 8.5 liters. Check out the units. Liters cancel, moles cancel, Kelvins cancel. If you check your units and you've got like millimeters of mercury, that doesn't cancel atmospheres. You need to take your pressure out, change it to the correct unit, and stick it back in. 0.55 times 0.0821 times 306 divided by 8.5. Pressure equals, here I've got a couple of numbers with only 2 sig figs. So my answer is going to have 2 significant figures, 1.625 atmospheres. And so 1.6 atmospheres is my answer. Any questions? Variations on a theme. That's what gas laws are. Okay, so the last two gas law problems we did, the ideal gas law problems, were very nice because the units were correct. So here's one where we have to do some unit converting. So how much volume does 0.556 moles of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees Celsius? So 0.556, you can use the table method. If you want to do that, go right ahead. So that's N, the number of moles. The pressure, 715 millimeters of mercury. The temperature is 58 degrees Celsius. They're asking me for the volume. PV equals nRT. Okay, V equals nRT over P. Oops, no, I didn't want to do that either. Yeah, you had a question?
If I could convert millimeters of mercury to ATM,
Mm-hmm.
would we use 760?
Yep. Get rid of that random thing here. We need R. The units on R tell me what my other units have to be. I need liters, atmospheres, moles, and kelvins. I've got moles, millimeters of mercury, and degrees Celsius. The moles are fine, but millimeters of mercury is not fine. So I need to convert this to atmospheres. I want atmospheres and millimeters of mercury down here. And the relationship you get from the table. But you can save yourself a lot of time if you memorize it, because we're going to do this conversion between atmospheres and millimeters of mercury, or torr, a lot. 1 atmosphere is 760 millimeters of mercury. So 715 divided by 760. Do not round everything off yet. We're not done. So 715 has 3 sig figs. So there's my 3 significant figures in my pressure. Write down the next 2 digits and carry those along with you. Atmospheres. Temperature, I have to convert that to Kelvin. Add 273. You can add the 0.15 if you like. 273. 331 Kelvin. These are the units that are in the ideal gas constant. So I'm finding volume. So I want N, 0.556 moles, R, 0.0821 liters times atmospheres divided by moles times Kelvin. And then the temperature in Kelvin, 331 Kelvin. And I'm going to divide all of that by the pressure, 0.94078 atmospheres. I check my units. Moles cancel, atmospheres cancel, kelvins cancel. 0.556 times 0.0821 times 331 divided by 0.94078 equals, looking at, I think I should have 3 sig figs, because when we convert this Celsius temperature with 2 sig figs into Kelvin, we have 3 sig figs now. So 3 sig figs in my final answer here. 16.060 is the volume, liters. And so that would round to 16.1 liters, because My decider here tells me I need to round the 0 up to a 1. Any questions? So we can use the ideal gas law. Oh, this slide has problems. We can use the ideal gas law in with mass measurements. There's either an extra word or words missing. We can use the ideal gas law and mass measurements to calculate the molar mass of a gas. In combination, yeah, that'd probably be good. Will I remember to fix this after lecture? Probably not. So let's look at how we might do that. A sample of gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. Well, what is molar mass?
Great.
Grams. It's the mass of how much? Of 1 mole, right? So it's the mass of 1 mole. So it has units. It's sometimes abbreviated capital M, molar mass. It has units of grams per mole, right? So if we knew how much 1 mole weighed, we'd be done. Or if we knew the mass and the number of moles, we could take the mass and divide by the moles, right? Because if it was 2 moles, and we knew what the mass of 2 moles was, we would just divide by the 2. So what we need is the mass of this sample, and we need to know how many moles are in it. Well, they told us the mass. It's not in grams, though. We could convert it to grams, though, couldn't we? 38.8 milligrams. So I'm going to multiply by grams, divide by milligrams. Milli means 10 to the minus 3. Milli's in the denominator. I'm going to put what it means in the numerator, 10 to the minus 3. So this is going to be 0.0388 grams. So I converted the mass to grams. Now I need to find how many moles of gas are in that sample. Well, let's take those numbers and see what we've got here. We've got 224 milliliters. That's a volume. I've got a temperature that's 55 degrees Celsius. And I have a pressure that is 886 torr. That's looking like I could probably use the ideal gas law to find the number of moles. Are these good units to use in the ideal gas law, though? No, they're not. I need liters, atmospheres, moles, and kelvins. So I need to convert milliliters to liters. So that's going to be 0.224 liters. I need to convert Celsius to Kelvin. .328. And torr, I need to convert to atmospheres. Torr is just a different name for millimeters of mercury. 1 atmosphere is 760 torr. So 886 divided by 760. 1.16. That pressure had 3 significant figures. And so when I divide, I still need to have 3 significant figures, but I'm going to carry 2 extra digits to avoid rounding errors. So I've got liters, kelvins, and atmospheres. And so now I can use my ideal gas law. The PV equals nRT. And if I rearrange that to solve for N, I get N equals PV over RT. So N is the pressure, 1.1657 atmospheres, times the volume, 0.224 liters, divided by R, 0.0821 liters, atmospheres per mole, Kelvin. And the other thing down there is the temperature, 328 Kelvin. Now, doing this on your calculator, I've got two numbers in the denominator. So if you like to multiply, use parentheses. 1.1657 times 0.224 divided by, use the parentheses, 0.0821 times 328, close the parentheses, equals N equals 0.00. I should have three significant figures here. 9, 6, 9. Those are my three sig figs. Leading zeros don't count. Write down two extra digits, that many moles. There's my number of moles, and there's my mass. So I'm going to take the mass of this sample and divide by the number of moles in this sample. So 0.0388 divided by 0.0096965 equals. And this should have three significant figures, 4.0014. The units are grams per mole. And when I round that, I get 4.00 grams per mole. Can you tell what gas that is? It's helium. Helium has a molar mass of 4.00 grams per mole. Yes?
Would you ever have to convert grams to one mole, like use the molar mass as a conversion, or do you always find the molar mass?
Well, if you're finding the molar mass, you can't use the molar mass to convert anything.
Well, we have both.
Well, there are other questions where you're given a mass and you need moles, and you use the molar mass to convert. And you might, like if they ask you the mass of a gas, the volume of a gas under certain conditions and they give you its mass, they'd have to tell you what kind of gas it is so that you could use its molar mass. So this is the molar mass of helium. What's the smallest molar mass you could have? 1. If you had atomic hydrogen, which hydrogen does not like to be, but if you had atoms of hydrogen, the molar mass would be 1 gram per mole. If you end up with something smaller than that, you did something wrong. Okay? You can't have anything smaller than hydrogen. Okay, a sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 976 millimeters of mercury. Find its molar mass. Yeah. So let's label our stuff. So we're finding molar mass. So the mass of our sample is 827 milligrams. The volume is 0.270 liters. The temperature is 88 degrees Celsius. The pressure is 976 millimeters of mercury. To find the molar mass, we need the mass of the sample, and we need the number of moles. Well, here's the mass. It's in milligrams. Let's convert that. Milligrams on the bottom, 10 to the minus 3 grams on the top. .827 grams. We've got a gas, and we need moles. We don't have anything changing. We're going to use the ideal gas law. So we need to get these units, the correct units. Liters is good, but Celsius is not okay. So we convert this to Kelvin. .361 Kelvin. Pressure needs to be in atmospheres. So millimeters of mercury in the denominator, 1 atmosphere is 760 millimeters of mercury. So this is 1.2842 atmospheres. PV equals nRT, N equals PV over RT. So pressure, 1.2842 atmospheres, times the volume, 0.270 liters, divided by R, 0.0821 liter atmospheres. See, I blessed you guys all day, so I'm not saying it anymore. And the temperature, 361 Kelvin. Plug that into your calculator. We'll see if we can get the same number. I'm getting 0.011698 moles. You get that? If you got a really big number, you're miscommunicating with your calculator. It has to do with the dividing by 2 terms business. Making space. So we were trying to find the molar mass. The molar mass is the mass in grams divided by the number of moles. So the mass was 0.827 grams, and we divide by the number of moles. Whoops, 11698 moles. 0.827 divided by 0.011698. 70.695 grams per mole. 3 sig figs, so that ends up being 70.7 grams per mole. Is that a possible molar mass of the gas? Sure it is. It's bigger than 1, and it's not 50 gazillion. So, probably fine. Any questions?
Will we be asked like what gas?
You could be asked what gas it is. You would either be given, a limited number of choices. So if it was multiple choice, how would you figure out which one it was? Well, you'd calculate the molar mass of each of them and see which one it matches up to. Or it could be an element. If it's an element, then you'd look on the periodic table. So the closest one to 70 would be gallium, which is a metal. It's not a gas. At 88 degrees Celsius, that's pretty hot, but not hot enough to vaporize a metal. Or it could be a diatomic element. It could be chlorine. Probably is chlorine. Because chlorine's diatomic, chlorine's 35.45. You double that and you get 70.5. So it's probably chlorine. Did that, okay. So gas behavior depends on conditions. We're assuming, we've been using this ideal gas law, we're assuming that gases behave ideally. Well, do they always? No, of course they don't. So good conditions for gases to behave like we expect them to are high temperature and low pressure. So at a high temperature, the particles are moving quickly. That means that when they bump into each other, they're not going to interact with each other very much at all. At a low pressure, there's a lot of empty space. And so the size of the particle is not going to be important because there's so much empty space. When we go to a low temperature and a high pressure, low temperature now, the gas molecules are moving more slowly. When they bump into each other, they're more likely to kind of stick to each other or repel each other, but they're going to behave a little differently because they're going to actually interact with each other. And then under a high pressure situation, things are getting really close, and now the size of the molecules or particles is starting to matter. So if you think about, say, 5 guys in this classroom, does it matter if they are gymnasts or defensive line football players? No. Put those same 5 guys in our elevator. Have you been in that elevator? It's pretty small. Is the size of the guys going to matter now? Gymnasts tend to be fairly short and very slim, right? Muscular, but very slim. Linebackers, big. They're tall and they're wide, right? Now the size is going to matter because they're in a small area. So that's like a gas under high pressure. The size of the particles matter. So when we have low temperatures and high pressures, then the ideal gas law doesn't work very well. But in Chem 3A, we can just ignore those situations. Just know that they exist.